All right. Well, thank you, Santosh. And I also want to thank the Dynamic Systems and Controls Division Executive Committee for this recognition as the Nyquist Lecturer for 2020. As you will hear in my talk, the DSCC, well, it was the winter annual meeting back then, was the first academic conference that I attended as a graduate student. It really is an honor to be recognized by the community that I consider to be my intellectual home. In 2005, I sat near the front of the room to listen to Carl Astrom give his first Nyquist lecture. I was fascinated by his ability to intertwine history in his talk about Nyquist's contributions to our field, and I've tried to emulate that approach with my talk today. Before I get started though, I want to thank my amazing lab, my current PhD, master's, and undergraduate students, and of course the sources of support for our research, and the outstanding group of alumni from the Mahi Lab who have contributed to the work that I'll highlight today. The title of my talk, Haptics, a Hot Topic with Controls at its Core, is in reference to Professor Wayne Book's Nyquist lecture 10 years ago. Wayne has been a longtime mentor and friend, and I hope that I too can be retired and fly fishing in my free time 10 years after giving this talk. Just kidding. All right, let's dive in. I have 3 objectives for today. First, I will introduce the fundamental ideas of haptics and tell some stories about how this research topic emerged from this very research community. Then I will discuss a few core dynamic systems and controls concepts that have framed much of the fundamental research in haptics in the past 20 years. Finally, I will highlight a few emerging future challenges in the field that offer an opportunity for us to bring our experience to bear and advance the field in the coming decades. So let's start with some history. So the word haptic, according to Merriam-Webster, comes from the Greek haptesthai, meaning to touch. It entered the English language in the late 19th century as a medical synonym for the word tactile. In their 1996 Robotica paper, Ellis, Ismail, and Lipset defined haptics as follows. They said, the haptic system in humans includes proprioceptive sensing of muscle tendon states, as well as tactile sensing of skin deformation. Interestingly, they noted in this early paper that the role of human perceptual processes in understanding the haptic sense. They went on to clarify that for many tasks, proprioceptive and tactile information is integrated early in the sensing process, and so it is proper to speak of the system as a whole when a human hand or arm interacts with the environment. They went on to note the potential that haptic interfaces presented to the broad field of robotics research, stating, and this is a quote, "One intriguing theme in robotics research is the construction of a haptic interface, a device that can sense human operators' hand motion and actuate the operator with forces or torques without significantly impeding the hand motion." Touch is often overlooked in our current computer interfaces, though more and more portable and wearable devices are incorporating haptic notifications. Perhaps the current pandemic has made you realize the importance of touch interactions, be it a fist bump, a handshake, or a hug. Our sense of touch is unique among our senses. It gives us a bidirectional way of interacting with our environment. We see hummingbirds in flight, we hear a beautiful symphony, and we can taste the delicious flavors of freshly picked berries. But these senses are unidirectional. When we see, taste, or smell, we don't change our environment, we only experience it. What's interesting about touch is it's bidirectional. The earliest realizations of haptic kinesthetic interactions came in the form of flight simulators, which sought to recreate the dynamics of aircraft behavior and study pilot-induced oscillations. So in the late 1980s and early 1990s, the dynamic systems and controls community was advancing a new field of research, built in part on the foundational work of Neville Hogan and his 1985 publications in the ASME Journal of Dynamic Systems Measurement and Control. You might be familiar with these papers. The focus was on the design and control of devices that enable humans to interact with virtual and remote environments. It just so happens that while Neville was busy working on his impedance control papers, a couple of MIT graduate students, both under Hogan's advisement, were forging lifelong friendships as they carried out their PhD research. So Ed Colgate was one of Neville Hogan's PhD students, and another member of our community, the late Carl Hedrick, served on Ed's thesis committee. The title of Ed's thesis, completed in 1988, was The Control of Dynamically Interacting Systems. In a nearby lab, Dov Adelstein was working with Professor Mike Rosen, and that same Neville Hogan was a member of Dov's PhD committee. Dov's thesis was entitled A Virtual Environment System for the Study of Human Arm Tremor, and it was completed in 1989. So after Ed and Dov completed their studies at MIT, Ed started out as a professor at Northwestern, and Dov joined the research group at NASA Ames. As young academic researchers do, they looked to their professional society and the conferences they had attended as graduate students for ways to get engaged. They were both fairly active in the ASME Dynamic Systems and Controls Division Robotics Technical Panel, and so they decided to organize a technical session at the 1992 ASME Winter Annual Meeting, or WAM, which was held in Anaheim that year. Right. So they reached out to their friends. It was a bit MIT-centric. Lynette Jones and Ian Hunter, Will Durfee, Hong Tan, Nat Durlick, all of these folks contributed papers, and as you do, Ed and Dov submitted their own work to their session. They organized 9 papers into a session that they titled Issues in the Development of Kinesthetic Displays of Teleoperation in Virtual Environments. It's a lot of words, but what's interesting is that despite the title of this session being hardware focused, right, the development of these kinesthetic displays, the papers within the session reflected the interdisciplinary nature of haptics research that was characteristic of the field from the very beginning. Of course, there are papers on device design and control design, but there's also papers about modeling human arm movements and manual control and human operator perception. Ed and Dov had so much fun organizing that 1992 session that they did it again in 1993. This year, they got nearly double the papers, broader participation, and they changed the title of the symposium. This is the first appearance of the word haptic related to technical sessions at the ASME Winter Annual Meeting. It was called Haptic Interfaces for Virtual Environments and Teleoperator Systems. Still, the session focused on areas that were core DSC topics, like hardware design and evaluation and stability, plus the interdisciplinary aspect of haptics was present, again, highlighting research trends that are hot still today. For example, there's a paper about human operator adaptation to machine instability, which is a very common topic that we're still addressing in physical human-robot interaction. There was a presentation by Juan Michael Goldfarb, happens to be my PhD advisor, on the design of wearable orthoses for applying loads to lower limbs, precursor to the burgeoning field of rehab robotics and exoskeletons. And there was papers on novel materials and actuators, shape memory alloys, for providing tactile feedback. So fast forward 3 years, and I would attend my very first ASME Winter Annual Meeting, my very first haptics symposium as a first-year graduate student at Vanderbilt. This was my introduction to the DSC community, and I instantly saw the influence that all aspects of our field were having on the growing research in the field of haptics. So if you just take a look at this slide, what you see is all of the different sessions were themed. We have transportation systems, modeling, sensing, and control for manufacturing processes, precision machine control, haptic interfaces, impedance planning, robotics, biomechanical systems. So all of these were intertwined. So while these sessions of haptics were going on, all around them in the rooms, as we would expect at a large conference, were presentations and papers about sort of these fundamental foundational concepts in dynamic systems and controls that clearly influenced the early field of haptics. Time permitting, I can share the list of organizers of the sessions featured that year in 1996. It's a veritable who's who of the DSC division. So a conference paper that appeared in the 1993 Winter Annual Meeting was expanded into a seminal paper published in 1996 in the journal Robotica by Ellis, Ismail, and Lipset. This paper highlighted applications of haptic interfaces, and importantly, it laid out the design trade-offs and control challenges for our field. These ideas framed much of the fundamental research in haptics from the early 1990s up to today. These authors identified 4 potential applications of a haptic interface, which I highlight with videos of research from my own lab at Rice. In the top left, teleoperation of a remote robot, here demonstrated with Rice haptic paddles that we use for teaching undergraduate dynamic systems concepts. In the top right, characterization of human motor performance, here demonstrated how we, let me click that video. That one doesn't seem to want to run. All right, we'll try it again. We'll give it one more go. If not, we'll just let it be. Anyway, characterizing human motor performance where we simulate complex dynamic systems to be manipulated to achieve some goal. It was also envisioned that a potential application of a haptic interface might be for conducting psychophysical experiments on haptics. This was a significant focus of my own PhD work done at Vanderbilt with a custom 3 degree of freedom haptic device shown in the bottom right of my slide. And finally, interaction of a human with a virtual environment can be enabled by adding haptics, allowing the user here to feel forces and torques for a task of swing up of a pendulum using our Mahi open wrist. This paper also identified specific application tasks for teleoperation, including handling materials in hazardous environments and remotely operating in an environment in which safe human presence is expensive to achieve and maintain. So I demonstrate this with a slide featuring space teleoperation system developed by the European Space Agency. This is the ACTOR Advanced Teleoperation Control Station and LWR and Task Board work cell. And finally, another application task for teleoperation was identified as amplifying or reducing human scale motions and forces. The Da Vinci surgical robot that I'm sure you're familiar with from Intuitive is one such system that can filter tremor and magnify human movements to enable precise surgical procedures. So all of these applications share the requirement that the operator be as unimpeded as possible in motion while they're holding the device, yet be provided with forces and torques that are of high fidelity. So as I'm moving around in my virtual environment, I want free space to feel free. But when I come in contact with virtual objects, I want them to be as crisp and the forces to be as high as possible to make it feel like a physical environment that I would experience in the real world. Ellis et al. Went on to identify the following list of design objectives for any high-performance haptic interface: low apparent mass and inertia, low friction, high structural stiffness, backdrivability, zero or at least very low backlash, high force bandwidth, the absence of mechanical singularities, high force dynamic range, compactness, and an even feel through the workspace. These guidelines, while often conflicting and difficult to achieve, led to the use of stiff and lightweight materials like carbon fiber, the development of lots of parallel manipulators as haptic devices, the use of capstan transmissions that are backlash-free, and novel control approaches, all of these realized over the next 2 decades of haptics research. This chart, courtesy of Gosselin, shows a range of commercially available grounded kinesthetic haptic devices developed since the early 90s. Grounded devices sit on a floor or a desktop where the user grabs the handle or stylus to interact with the remote or virtual world. On the x-axis are plotted the force output capabilities of each commercial device, while the y-axis plots the workspace. And so you can see this significant cluster in the bottom left of the slide, where we have fairly small workspace devices with fairly low forces, but a few outliers that are able to achieve larger workspace through a wearable format like Immersion's Cyber Glove, or admittance-based devices that enable larger workspace that I'll talk about a little bit later. So now that you have a sense of how this field began, let's discuss some of the core dynamic systems and controls concepts that framed much of the fundamental research in kinesthetic haptics from around 1990 to today. First, a primer on kinesthetic haptic devices. They come in 2 forms, impedance type and admittance type. Here's a diagram of an impedance type haptic display. User motion is sensed by the device, force is computed as a function of position, and the haptic device then outputs a force that the user feels. For example, we might want to simulate a spring, so the computed force would be a scalar multiple of the user's motion, so they can feel that stiffness of the object. And we can put other elements into our algorithms to compute those forces so that we get the experience in the virtual environment that we seek. Most force feedback devices are of this impedance type. The alternative implementation is an admittance type kinesthetic device. Here the user applies a force to the haptic device. Force sensors on the device are necessary, and the desired position is computed as a function of that force. Then the haptic device commands a desired output position, and the user feels the resultant motion. These devices are not as common, but they do enable larger workspace devices, and we're able to implement all of our position control techniques that we are familiar with from our field. So a typical kinesthetic haptic system is comprised of a human holding some haptic device. Here I show the Mahi open wrist. This device provides motion as the user interacts with it, which is sensed and processed by the mechatronics interface. A computer then carries out the haptic rendering, determining the force that the user should feel based on their motion. Again, the mechatronics interface converts this digital force command to a physical force that the user feels as the motors of the haptic device are controlled. This system has two primary subcomponents. The mechanical device, human, and mechatronics interface contribute to the physical system dynamics, and the mechatronics interface together with the computer perform the haptic rendering based on pre-programmed algorithms. So when we couple a human to a robot device, it is important to ensure that the overall system behavior is stable. Often we use passivity, a more conservative requirement, to analyze haptic system stability. So why does instabilities occur? Well, when we're holding on to this haptic device, if we were interacting with the real world, we can only approximate those in the virtual world, right? So real world interactions are only approximated in the virtual world by our computational models. And although our approximation errors are small, their potentially non-passive nature can have profound effects on that physical experience that the user has. So consider a haptic device, and we'll model that haptic device to have some mass and inherent damping. And that haptic device is rendering a virtual spring of stiffness K. Stability would require the roots of the characteristic equation to have negative real parts. Since the mass and the damping are defined by our choice of physical hardware or our design of our haptic device, we then can modulate K, the stiffness of the virtual spring, to ensure stability. However, the choice of K influences the fidelity of our virtual world. Higher K in my virtual world means stiffer, more realistic surfaces, so I really want to drive that K to be a large number. However, we can see from the left-hand plot, as I increase K, I push the limits of stability with my system. And the result is not always pretty. So here's a phantom premium that's rendering a virtual wall with a stiffness of increasing values. That's 50 newtons per meter now. And you can see that once we reach a large stiffness, in this case 100 newtons per meter, then we get an unstable behavior of the haptic device bouncing on the virtual surface. And then the graduate student has to intervene. So let's remember what Ellis et al. Told us. We have these objectives of low apparent mass and inertia, low friction, high structural stiffness, backdrivability, zero or very low backlash, high force bandwidth, the absence of singularities, high force dynamic range, this even feel through the workspace. All of this is often represented by examining what we call the impedance width, or Z width, the dynamic range of impedances that can be rendered with a haptic display while maintaining passivity. In the figure on the left, we have a frequency domain representation of Z width. The x-axis would be the frequency of the input motion generated by the human. And so we're within the achievable range of frequencies up to about 100 radians per second at the very extreme that humans might be able to provide. And then the y-axis is the magnitude of impedances that can be passively rendered. Now we want near zero impedance in free space. So the bottom line, we're really trying to push that down as far as possible. But we also want high impedance at low frequencies when we come in contact with our virtual surfaces. So we want to push that upper bound up as far as possible. Another way to visualize this is with the plot shown at right, which shows the virtual stiffness versus virtual damping that can be experimentally implemented and still maintain passive interactions. This is what we call a Z-width plot. So on the y-axis are the virtual stiffness values for my environment's virtual walls. And on the x-axis are the damping coefficients, the damping values of those virtual walls. And we can look at pairs of those and then experimentally interact with those virtual surfaces and see if the behavior is passive or not. So Any combinations of virtual stiffness and damping that lie under these lines would indicate passive interactions, while those above the lines or outside of those lines would be non-passive. This plot by Colgate and Brown, published in 1994, explored the addition of physical damping to the haptic device as a means to increase Z-width. Now, most of our haptic devices are implemented as sampled data systems. And again, that guy Colgate explored how the sampled nature of our haptic device implementation might affect stability of haptic interactions. So here we have a manipulandum held by a user inputting some motion. The block diagram illustrates the zero order hold that is required due to the computational implementation of the haptic rendering of a unilateral constraint or virtual spring. So the block diagram models our operator. Our operator provides some input and some motion, converted through the dynamics of the user's arm, results in some force, right? This 1 over ms plus b is a model of the dynamics of our haptic device itself. We can take that resultant velocity and convert it to position. This t represents the sampling period. And so my sampled position value x of s is then subjected to this unilateral constraint. This is our virtual spring implemented in our haptic virtual environment represented by the h of z. And then the zero order hold means that there's a 1 time period delay before I can implement my commanded resultant force onto the haptic device. So in 2008, Ware and Colgate showed that a necessary and sufficient condition for passivity is that the physical damping of the device must be greater than this function of sampling period, the frequency of the input motion, the virtual environment to be rendered, and the Nyquist frequency. Did you see that? I had to mention Nyquist frequency in my Nyquist lecture. All right, task complete. So they went on to show in this paper that if the virtual environment is a virtual wall with some stiffness K and damping B, represented by the discrete time transfer function h of z, assuming that the velocity estimate comes from a backward difference differentiation, then the requirement on passivity is that the physical damping of my haptic device B must be greater than the virtual stiffness K times the sampling period T over 2 plus the absolute value of the virtual damping. So with this work, we now had a straightforward way to ensure stable interactions between our users and our virtual walls. And it is clearly a function of the physical device, the haptic device itself, this lowercase b being the fact that this physical device needed to have some inherent damping to ensure passivity, the computational implementation implied by the sampling period T, and the parameters of the virtual wall, capital K and capital B, that we wish to render. Abbott and Okamura further extended this work to show that the maximum virtual stiffness must be less than the minimum of 2b over T, where B is the device damping, T is the sampling period, or 2fc over delta, where we might have some friction and we have sensor quantization, the quantization of position due to an encoder. Because many devices, haptic devices, have high resolution encoders, the sampling rate can still be a limiting factor. So we go back to this equation. The limiting factor could be the delta, the quantization of the encoder position that we're sensing, or the limitation could be the sampling period T. As before, in this video, we increase the stiffness of a virtual floor until instabilities are induced. This is first implemented with a sampling rate of 1 kilohertz. Then we show that the computational platform can be improved. Here we used FPGA to render a virtual wall with increasing stiffness at a sampling rate of 20,000 hertz, 20 kilohertz. This allowed us to significantly increase the virtual wall stiffness that could be stably rendered. So now we're at 100 newtons per meter, and we can even extend well beyond that to 500 newtons per meter, which is well beyond what we were able to implement with only a 1 kilohertz sampling rate. In my own lab, we've also looked at computational methods for determining endpoint velocities and how this can affect Z-width. If we want to implement a virtual wall that has both stiffness and damping, we're measuring the motion, the position of our haptic device, and often we're computing the derivative in this sample data system. Finite difference methods often require filtering, which can introduce delays. We explored the use of Lavant's differentiator to extend Z-width compared to finite difference methods in this work back in 2018 with two of my former PhD students, Vinay Chadha and Oskan Chelik. So you can see that Ellis and Ismail defined our holy grail for haptic devices way back in that 1993 WHAM paper and the subsequent Robotica paper of 1996. Low apparent mass and inertia, low friction, high structural stiffness, backdrivability, zero backlash, high force bandwidth, high force dynamic range. So what can be done to improve your Z-width and approach this ideal goal? So one approach is to look at the physical hardware itself. We can design our hardware in a particular way, or we can modify our hardware, perhaps by adding damping, either physical or virtual. We can improve the encoder resolution or increase the sampling rate, or we can improve velocity estimation techniques. All of these will improve the Z-width or the range of impedances that I can display with my haptic device. Now, due to time limitations with my talk today, I can't go into other methods, but it is also possible to improve your Z-width with control using passivity observer and passivity controller techniques or prediction compensation techniques, or you can reduce your virtual environment impedance and fidelity to stay within a safe range. This approach, while it sounds sort of counterintuitive, why would you want to decrease the fidelity of your display, actually takes advantage of the limits of human perception to create illusions of higher performance with visual feedback or other tricks that can fool our perceptual ability. So we can maintain stable interactions through the physical interplay, the touch interactions, but use visual feedback to fool the user, to play off their perceptual limitations and increase the apparent fidelity of the system. So let's sort of travel back in time again and recall that in parallel to this fundamental work on the design and control of haptic devices, researchers were beginning to explore how to use such devices to rehabilitate motor coordination following stroke. So this slide shows two different devices for upper limb rehabilitation. On the left is the MIT Manus. This is an impedance type haptic device. And on the right is the MIME, which was actually a Puma industrial robot, a Puma 560, which was converted to be used as an admittance type haptic display. There's a 6-axis force torque sensor at the interface between the patient's forearm and the end effector of the robot. And so you could use force sensing of the user's motion, control the position of the robot to implement different rehabilitation scenarios or movements. This enabled an individual with stroke to interact with physical objects, even if they had decreased motor function, or as in the case of the MIT Manus here, allowing a user to do virtual rehabilitation tasks through the Manus device. Starting in the early 2000s, work on rehabilitation expanded, and researchers started looking at not just how haptic devices could be used to rehabilitate those with motor impairment, but how haptic devices could be used to train new motor skills. And this has been a significant area of focus in my research lab at Rice. Haptics has long been recognized for its potential in virtual or augmented training applications, and there's strong evidence that haptics can enhance performance of dynamic tasks performed in virtual reality. In my group, we've been developing haptic devices that can guide users to learn new tasks, especially training with haptic feedback in virtual environments. We're also in the early stages of translating our methods to training for endovascular surgeons using robotic platforms. I'll share with you one example of how the physical interaction between the robot and the human can guide the human to improve task performance. In this work, we used an impedance type haptic device, our Mahi open wrist, shown with the handle on the right-hand side. And we compared different types of haptic guidance to see how they affected the user's ability to learn to control this double pendulum to follow a specific desired trajectory. Now, as the user interacts with the virtual environment, they're feeling the forces and torques of the dynamics of the pendulum through the haptic device. And then we explored our different ways to provide guidance to instruct the user to follow this precise desired trajectory, which is indicated with the black dot moving along the sphere. So we shielded the user's view of guidance and obscured it from their view. We looked at one condition where the guidance was provided on top of the haptic feedback they were feeling of the task. So as they manipulated the device, they were feeling the forces and torques of the pendulum, but they were also feeling cutaneous cues with this band around the forearm that would show them how to steer the haptic device to achieve the desired trajectory. In a second condition, we put that steering cue on the contralateral arm. And we also compared kinesthetic guidance provided with a second kinesthetic type impedance-based haptic device where the guidance forces that are showing them how to steer the joystick are provided on the left, and they're feeling the task dynamics of the double pendulum on the right-hand side. We found that using this approach, performance improved with haptic guidance since the user could feel the task dynamics and they could feel how they should change their control of the 3D joystick to more accurately track the trajectory. So we used our 3 degree of freedom haptic device, the Mahi open wrist, which is impedance controlled, to simulate the dynamics of that double pendulum, trajectory following task. And by tracking the user input and providing intuitive haptic feedback based on user performance, we provide guidance forces through the haptic device or through a wearable device, this cutaneous twisting band, to guide the user. Now, there's a lot under the hood of just this approach as well in terms of different control algorithms, whether you provide disturbance forces to train new skills, whether you provide assistive forces that pull somebody along a desired trajectory, and also in the rehabilitation domain, how we can in real time model and adapt a model of a user's changing capability to adjust the support provided by the robot to achieve these movement goals. All of this is more than I have time to go in today, but I think you find it quite interesting to see, again, the fundamentals of dynamic systems and controls that are under the hood of these haptic devices, either to create these high fidelity virtual environments or to give us insight into how we might use the forces and torques from the haptic device to guide and manipulate the user to retrain skills or train new skills. So as my time is drawing to a close, I want to wrap up by proposing some of the emerging future challenges in the field of haptics that provide opportunities for our dynamic systems and controls community to contribute. So as you've heard, when I started in the field of haptics in the late 1990s, the focus was on the design of grounded haptic devices and rendering of kinesthetic type haptic feedback. These are the forces and torques that are experienced as you explore the world, touching objects, feeling weight or stiffness or compliance. Many of these early devices relied on a stylus as the interaction point between you and the virtual world that you were feeling, like exploring the world through dental tools. A decade or so later, with the advent of tablets and smartphones, haptic research started to shift to focus on surface haptics, or how to convey textures and tactile sensations through the fingertip exploring the surface. This is done either by vibrating the surface to modulate the friction between the fingertip and the surface, or using electrostatics, or even using an array of pins that can be individually actuated to create a three-dimensional surface. More recently, we've seen an explosion in wearable devices, and more of these devices are providing haptic feedback. You might receive different vibration notifications indicating that you're receiving a phone call or that you should stand up and take a walk. My group, along with other groups around the world, is interested in enhancing the range and type of haptic feedback that can be provided with wearable devices so that we can move beyond simple notifications and use these for navigation and communication, conveying really information-rich messages through different types of haptic cues conveyed directly to the skin. So what are some of the challenges? In thinking about surface haptics or touchscreen devices, we can look at this image here of digital clay. So we've got a rendering of what an array of these linear actuators might be able to display as a surface that can modulate. But there's inherent control challenges. How do we control large arrays of actuators? And what's the scalability of this kind of a display? With surface haptics, these variable friction devices, you can create the friction texture sensation through electrostatic vibration or ultrasonic vibration of the screen, but it's challenging to be able to do this with multi-touch. We can often do this with the finger at a single point on the screen, and we're just now seeing advances in haptics where multi-touch is possible, where you can get different effects at different points on the screen. Another emerging area of haptic interactions is mid-air or in-air interactions, using ultrasonic or acoustic radiation pressure to actually generate touch sensations on the hand as it moves over an array of ultrasonic actuation. Another challenge that's not illustrated in this slide is texture modeling. Our traditional kinesthetic devices don't have the bandwidth to accurately recreate high frequency vibrations. They're very good at sort of the low frequency vibrations when we come in contact with objects, but everything sort of feels like a thud. We want crisp interactions as if I was tapping on the surface. And that high frequency feedback is difficult to do with these traditional kinesthetic devices. They just don't have the bandwidth. So there are other techniques that are being explored for how we can overlay vibration feedback on a kinesthetic device, or come up with new techniques for texture modeling. So not only can we feel smooth surfaces, but we can feel surfaces that have varying textures and interesting characteristics. On the wearables side, some of the challenges remain portable power and computing, miniaturization of actuators and sensors, but all of this now we want wearable. It's on this squishy interface that is our body. So how do we transmit those forces reliably? Often with these wearable haptic devices, as shown with the TASB bracelet in the top left corner, we lose the bidirectionality of these interactions. So no longer am I using a stylus or a handle to push and pull and interact with my environment. I'm simply displaying haptic cues onto the surface of the skin. Now this takes advantage of different kinds of mechanoreceptors that are in the skin that respond to different stimuli, primarily differences between low and high frequency vibrations or pressure. As we saw with haptic devices that are grounded or kinesthetic in nature, there are trade-offs in fidelity and cost and portability that harken back to the early challenges outlined by Ellis et al. In that paper from 1996. How do we do this now in a way that's portable and wearable on our limbs? Finally, there's a real desire for exoskeletons that conform to the body and have sufficient actuation to be able to carry the limb through movement, not just offset a little bit of metabolic cost. How do we package actuation and transmission systems in a way that's safe and portable, yet still has the torque output capabilities and the precision sensing capabilities to really be able to accurately estimate the pose of the arm in different orientations, or in the case of the assistive glove, to know the pose of the hand and be able to apply appropriate forces and torques to assist hand movements or augment function. So I had 3 objectives for today. First, I introduced the fundamental idea of haptics and told some stories about how this research topic emerged from this very research community. Then I discussed a few core dynamic systems and controls concepts that framed much of the fundamental research in haptics in the past 20 years. Finally, I highlighted a few emerging future challenges in the field of haptics that offer an opportunity for us to bring our expertise in dynamic systems and controls to bear and advance the field in the coming decades. Thank you for your attention, and I'm happy to take questions.